All right, this is lesson 6.1, part 1 over similar polygons. So we'll be looking at, in this lesson, how to determine if two figures are similar and how to use their similarity to help us find unknown lengths. So just to re-clarify, we've talked about this a little bit, but to clarify again, similarity is when figures have the same shape but not necessarily the same size. So as you see in this picture, these two trapezoids have the same shape of a trapezoid, but they're definitely not the same size. And so that's what it means for two things to be similar, because they are related in their shape but not necessarily their size. You can see that also in these figures, in these squares. This is a really common way to look at similarity is the terms of parts of each other, right? To put it inside of, and put one figure inside of the other. And so these are other examples of similar figures. But in this lesson, we'll be looking at more of the definition of similarity and what actually is defining these figures as similar. And it really comes down to two things. One, corresponding angles and corresponding side lengths. So in similar figures, the angles are going to be the same. The corresponding angles are going to be the same. So like in this figure ABC, this triangle ABC and this triangle DEF, angle A is corresponding to angle D. Angle B is corresponding to angle E, and angle C is corresponding to angle F. Okay? If I were to lay the blue triangle on top of the red triangle, that's where the angles would kind of match up, like what you see in this with this square here, when they're laid on top of each other. E is this angle down here, B is corresponding to F, C to G, and D to H. So the corresponding angles all have to be congruent to each other. So between the two figures, no matter their size, if they're similar, then their angles, their corresponding angles, are all congruent to each other. The side lengths won't be the same length, right? Because they can be different shapes, or not different shapes, different sizes. But they're going to have a common ratio. So the corresponding lengths like DE and AB here, you see between C and KC, that K is just that constant, what we call a scale factor, okay, or that's the ratio between them. And so the ratio of the corresponding side lengths are all the same. It's all this the same number, whatever it is, what we're looking at, calling it K here. So if I take whatever the side lengths of A, B, and C are, if I multiply them by that constant K, that is going to be the side lengths of the similar triangle. And so what we say that those are proportional, right? The side lengths are proportional to each other. So you'll look at an example of finding scale factor. We'll actually look at this example and we'll kind of break it down. We'll walk through this, but the idea is like, if given similar figures, can we identify what the scale factor is? What's that common ratio between the side lengths? Identify the congruent angles, and then write out a ratio statement. So we'll also look at an example where we use the fact that two figures are similar to find one of their unknown sides. Because if you know that the ratios are proportional to each other, then you can set up a proportion and solve for one of the unknowns. And so we'll look at that example as well. In this last example, we won't look at altogether, but it's in your notes. It's determining if these figures are similar or not. Is this figure here similar to this figure here in blue, and explaining why. And ultimately what you would find out is that they're not actually similar. If you looked at all of their side lengths, you would see that they're all proportional. They all have the scale factor of 2/3. But if you look at their angles don't match up, right? The angles of the blue figure are not congruent to the angles of the red figure, or rather the green figure here. And so the only angles that match up are angle A and angle K. And so all the angles have to be congruent to all the angles here, and because they're not, then they're not similar. Okay? So again, it has to be both. The side lengths have to be proportional, and the angles have to be congruent. So let's look at a little more closely at the two examples that I just showed you. So this is one of the examples in your notes where we're talking about similarity. So it says, in the diagram, triangle RST is similar to triangle XYZ. And remember, this symbol here means similar. Okay, so what this is saying is that all of the angles in this triangle are congruent to the corresponding angles here, and all of the side lengths here are proportional to the corresponding side lengths in triangle XYZ. So if A says find the scale factor. To find the scale factor, you need to identify what are the corresponding side lengths or corresponding sides. So let's start with XY in this triangle here. Okay? So XY is which side over here is it corresponding to? Okay. Well, sometimes it's already set up for you to figure that out, and sometimes you're going to have to kind of like mentally play with it or even redraw it sometimes to figure out where is this going to be. And so this one is already set up for us to where this base here is the same as this base here. You can also sometimes look at their side lengths, right? Because 12 here is the shortest side over here, and so RS is the shortest side over here. So if we know these are similar figures, then we know those are going to be corresponding sides. So XY is corresponding to RS. Now to figure out the scale factor, we look at XY has a length of 12, RS has a length of 20. And then if I reduce that, that's going to reduce down to 3/5 and divide both 12 and 20 by 4. And so that's the scale factor. But let's make sure that's the scale factor for all of them. That's the correct ratio for all of them, which it should be if these are similar, but we do need to verify that. All right, so we looked at the other sides of the two triangles, YZ corresponding to ST, ZX corresponding to TR, and looked at their lengths. And for both of those, we get a common ratio of 3/5. So our scale factor for these figures is 3/5. Okay, that you need to look at the corresponding sides and then find the ratio between them. All right, let's look at B. It says list all the pairs of congruent angles. So if you already know that which sides are corresponding to which, okay, it makes it a little easier to find the corresponding angles, right? So if we know XY is corresponding to RS, then I know R is going to correspond to X here. So if these are similar figures, then angle R is going to be congruent. Let's draw a better congruent symbol. Congruent to angle X. Okay. Angle S is going to be congruent to angle Y, and angle T is going to be congruent to angle Z. Okay. Again, just R and X are corresponding, T and Z are corresponding, S and Y are corresponding. And so those are the pairs of congruent angles for these two similar figures. It's really just wanting you to identify, okay, what's making these similar and which parts are corresponding or matching up to each other. And so that's what we'll also be doing in C as well, is writing the ratios of the corresponding side lengths in a statement of proportionality. It's similar to what we were doing up here, except we're not looking for the scale factor. We're just trying to write out that statement of saying that these are the sides that are corresponding and that are proportional to each other. So XY is corresponding to RS, and we know that they all have a scale factor of 3/5, and because these figures are similar, then all of these should be equal to each other. Okay? All of these ratios between side lengths should be equal to each other. So we'd say that's YZ over ST equal to ZX over TR. And that's what a statement of proportionality is just writing out, okay, which are the corresponding side lengths and are they actually proportional to each other. And we did verify that up here in A when we found they all had a scale factor of 3/5, or a common ratio of 3/5. So if you know that they're similar, that's what you can identify as their common scale factor, their ratio, which angles are congruent, and then which sides are corresponding in their statement of proportionality. All right, let's look at number 11. It says in the diagram, triangle DEF is similar to triangle MNP. Find the value of X. So if we know that these triangles are similar, then we know their angles are congruent and their side lengths are proportional. And we're looking for the unknown side length EF, which has a length of X. That's what we're looking for, is that value of X. So because we know that the side lengths are proportional, we can set up a proportion that involves X and then solve for it. So in this figure, I know MN is corresponding to DE. MN is corresponding to DE here. And so because these triangles are similar, I can say that that is equal to NP over EF, the ratio between NP and EF. And I wanted to include EF because that has X, right? So I need to include that. So that's how I know which side. It wouldn't have mattered. I could have done MN over DE, or I could have done MP over DF. Okay? It doesn't matter as long as you're consistent, but I did need to include EF and NP because EF has X, is the length of X. That's what we're looking for. NN over DE is equal to NP over EF. And now I'm just going to plug in the values for what those are, right? So MN has a length of 18, DE has a length of 15. NP has a length of X, what we're looking for. EF has a length, other way around. NP has a length of 30. EF has a length of X. And now I've set a proportion just based off of the corresponding sides and their ratios and their lengths here. Oops. And then I'm going to solve. So solve the proportion. 18 times X is 18X. 15 times 30 is 450. Divide by 18. X is equal to 25. And that'd be your answer. So that's the length of EF over here, 25. So that's how we can use the fact that these are similar figures to find that unknown sign length.